Okay, so to begin Chapter 11, Chapter 11 is about intermolecular forces, and that's really just another way of saying that it's about liquids and solids, because that's what distinguishes liquids and solids from gases, is the fact that gases basically have no intermolecular attractions, that is, no attractions between the particles that make up the overall substance, and liquids and solids do. Sorry. So gases have essentially no intermolecular attractions. Turns out liquids have moderate intermolecular attractions, and solids have really strong intermolecular attractions. And that is the fundamental difference. The biggest difference between solids, liquids, and gases is the strength of the intermolecular attractions. So how strongly attracted are the particles towards each other? The difference in intermolecular attractions leads to differences in density and other properties. In addition to state or phase. So solids and liquids are known as condensed states. And that's because the particles are close together. And things that are condensed state, like solids and liquids, tend to have relatively high densities. And that is relative to gases. The densities of solids and liquids can vary a lot. There's a very broad range of densities for solids and liquids, but they're all relatively dense compared to gases. Okay, so gases, on the other hand, are known as expanded states. And that is, the particles are not close together. As we saw, the part of the definition of an ideal gas, or a gas, according to the kinetic molecular theory of gases, is that the particles have to be essentially infinitely far apart relative to the size of the particles themselves. And so that is definitely an expanded state. And that means relatively low densities. One way that you can actually see that the densities of gases are much lower than the densities of liquids or solids is if you look at the units that are characteristically used for densities. For liquids and solids, for say solids, you generally have density given in units of grams per cubic centimeter. And for liquids, it's usually grams per milliliter. And we choose those units, as we often do, because they give us a convenient number to deal with, a number that's usually in the range of, say, from maybe 1 to 25 or 30 or something like that. So it's just convenient, normal size numbers. And keep in mind, remember also that a milliliter is the same thing as a cubic centimeter. So essentially, we're using the same units for measuring the densities of solids and liquids. For gases, we generally use a unit of grams per liter. We use a much larger volume for the densities of gases because if we measured the densities of most gases in grams per milliliter, we would end up with numbers like 0.001, which are too small to be conveniently dealt with on an everyday basis. Whereas if we measure it in grams per liter, it's more like 1 gram per liter. And so you can see the difference in the scale of the densities just by the units we use for measuring the densities of solids and liquids versus gases. You can compare the molar volumes also of a given substance like water in the 3 states in order to get an idea of the different densities. The molar volume of any gas at basically 25 degrees Celsius in 1 atmosphere is 22.4 liters, and water vapor is no exception. So 1 mole of water vapor has a volume of 22.4 liters, whereas 1 mole of liquid water has a volume of 18 milliliters. And that is, that's a huge difference between 18 milliliters and 22.4 liters. For solid water, ice, the molar volume is, I think, about 19.6 milliliters. So it's close to the molar volume of liquid water and way far away from the molar volume of the gas. Water is very unusual, as we'll see later in the chapter, in that the solid is less dense than the liquid. That is, when water freezes, the H2O molecules go into a crystal structure, which means that they're arranged in a certain way relative to each other. And in order to adopt that arrangement, the molecules actually have to move a little bit further apart than they normally are in liquid water. And so water actually expands and gets less dense as it turns solid, which is very unusual. It's the only common substance that does that. And that's the reason, for instance, that ice floats. And that has certain consequences too, which we'll go over that in more detail later in the chapter. There is a table early in the chapter, which goes over just a summary of the properties of various states of matter. And it would not be a bad idea to review that. Just it gives you sort of a good, quick comparison of solids, liquids, and gases. So for the 3 states, let me start with gas, since we've already done gases. So gas, liquid, and solid for the states. And then we'll qualitatively compare their densities, the shapes of objects or substances in those states, the volume of substances in those states, and the strength of their intermolecular attractions. For gases, well, we already said gases are called expanded states because they have low densities. So gases definitely have low densities, sorry. Liquids, on the other hand, relative to gases anyway, have high densities because the particles are close together, and that's because liquids have moderately strong intermolecular attractions, and that pulls the molecules in liquids closer together. Solids also have high density, and on the whole, their densities are actually a little bit higher than the densities of liquids. There are exceptions. There is some overlap between the densities of liquids and the densities of solids, but there's no overlap between the densities of liquids and solids versus gases. Those are like 2 completely different sorts of things. For shape, what we're talking about here is whether objects in those states have a definite shape or whether they can change shape easily. And so we would say that gases have an indefinite shape, since gases essentially really have no shape at all. The way we usually put it is the gases adopt whatever shape is the shape of the container that they're held in. And that's because of the tendency of gas particles to be in constant rapid motion in random directions. If you introduce even a very small gas sample into a very large container, those gas particles are zipping around so fast that they will eventually find the outer limits of that container and start bouncing off the walls. And essentially the gas has adopted the shape of the container that it's in by reaching the outer limits of the container almost instantly. Liquids also have indefinite shape. Unlike gases, they don't expand to fill the entire container, but at least up to the level of what volume there is, liquids will take the shape of their container. So if you take some water and pour it into a round glass, the water, like a cylindrical shaped glass, the water will be cylindrical in shape. If you take water and pour it into, say, a square bottle, then the water will take kind of a square shape like the bottle. And solids have definite shapes. So solids do not change shape easily. Probably the best you could do on getting a solid to adopt the shape of its container is if you were to take the solid and to smash it up into tiny little pieces, and then it might conform more or less to the shape of the container. But when we're talking about shape, we're really talking about at the level of individual atoms and molecules. So with liquids, if you take liquid water and pour it into a container, each individual H2O molecule is free to move relative to the others. And so that's what we mean when we say that it takes the shape of the container. The water molecules kind of slide over each other, and they find the outer reaches of the container. The same with gases. Each individual atom or molecule can move relative to the others, and so it completely adopts the shape of the container. With a solid, even if you try smashing the solid up into tiny little particles, each of those particles is going to contain billions and billions of individual atoms or molecules. And so it's not truly taking the shape of the container, because there are still, well, probably a majority actually of the atoms and molecules are still fixed in place relative to each other within each little grain of the solid. So that's what we mean by definite shape. For volume, gases have indefinite volume, meaning they will expand to fill the entire container that they're in. And again, it's because there are no attractions between the molecules in a gas, and the molecules in a gas are free to move relative to each other, and they're in constant, high-speed motion in random directions. And so when you put a gas sample into a container, the gas particles will immediately start moving apart from each other, and they will find the outer reaches of the container and start bouncing off the walls. And they'll be bouncing off the walls on all sides, including the top and the bottom. And that's what we mean by expanding to fill the container. And so that means an indefinite volume. On the other hand, liquids do take the shape of their container, but they don't expand to fill the container. So liquids have a definite volume, as do solids. And sort of last, but certainly not least, all of this is due to the strength of the intermolecular attractions. Gases have very weak intermolecular attractions, essentially none for all practical purposes. Liquids have moderate intermolecular attractions. The particles in a liquid are strongly attracted to each other enough that the particles cling to each other, but they're not fixed in place. So that's a liquid. Solids have relatively strong intermolecular attractions, and that just means that the particles are so strongly attracted to each other that they're not just close to each other, but they're essentially fixed in place, and they don't move relative to each other. Okay, so liquids and solids, because of their stronger intermolecular attractions, have much less freedom of movement. And that's due to the stronger intermolecular forces. And so to summarize what they actually can do, for liquids have vibrational freedom of movement. And that is, the particles can vibrate in place relative to one another. And they have translational freedom of movement. But their translational freedom of movement is somewhat limited just by the fact that the particles are so close to each other in a liquid. So there's limited translational freedom of movement. The particles in a gas are in constant, motion at really high speeds all over the place. But that's not actually the case for liquids. The particles in a liquid generally tend to move slowly relative to one another. And in fact, if you let a liquid sort of settle down without agitation, they hardly move at all relative to each other. And it's only when something happens to stir them up that they start moving translationally as well as vibrationally. For solids, it's vibrational only. Gases are easily compressed. And that's because the particles are far apart in a gas. And again, that's because these gases have essentially no intermolecular attractions at all. So there's no reason why they shouldn't be far apart. There's nothing attracting them to the other particles. So yeah, they'll be far apart. On the other hand, liquids and solids are not easily compressed. And that's because the particles are close to each other. And that, again, is because of their intermolecular attractions. In solids, the particles are basically touching each other. And in liquids, they're nearly touching, not quite. So essentially, liquids are a little bit compressible, and solids essentially not compressible at all. You may think of some solids that are compressible, like, say, styrofoam or something like that, but actually, styrofoam is compressible only because it has a lot of air spaces in it. So really, when you're squeezing a piece of styrofoam, or say a piece of cork or something like that, you're really just compressing the air within those air spaces. So it's a gas that you're compressing. The solid itself is actually not being compressed. Okay, solids can be crystalline or amorphous. Crystalline just means that the particles are arranged regularly. So there's a regular repeating pattern to the way the particles are arranged in a crystalline solid. And that repeats over and over again in 3 dimensions. And examples of some crystalline solids would be salt. Sodium chloride is a crystalline solid. And also diamond. Diamonds are crystalline. And that's because their particles arrange in a certain way relative to each other. And that same pattern repeats over and over and over again in 3 dimensions. Amorphous is from a Greek phrase that literally means without form or without shape. And that means a more or less random arrangement of particles in 3 dimensions. And an example of amorphous solids, well, one of the best known actually is glass. Glass is kind of an unpredictable sort of substance to deal with. You probably had experiences through childhood playing outside when a ball hits a window or something, and one time the ball can hit a window really hard and nothing happens, and some other time it barely touches it and the window shatters. And part of that is because of the fact that the particles in glass are arranged without any particular order. They're arranged essentially randomly relative to each other. And that means that some pieces of glass will have certain spots that are weaker than others. And so in one spot, the glass might be much stronger than it is in other spots. And it can react rather unpredictably. Others would be things like soot. Carbon, when it arranges itself in a crystalline pattern, you get diamond. But when carbon atoms are just sort of thrown in every which way, you get something like soot. And that would be another example of amorphous. Okay, so when we've got the phases of matter, we know that it's possible to change from one phase of matter to another. Or one state of matter to another, and those are known as phase changes. Some of them are really well known, like melting or boiling, and some of them are not all that well known, or at least not their scientific terms. And so I thought I'd take this opportunity to sort of summarize the names of all of the different processes that can take you from one phase of matter to another. So we've got solid and liquid and gas as the 3 phases of matter. And there are processes that will take you from one phase to another in both directions. So there are processes that, for instance, will take you from solid to liquid, and that would be known as melting. Or the more scientific word would be fusion, for going from solid to liquid. Going from liquid to gas, the more scientific term would be vaporization, but that's also known as boiling. And when you go from gas to liquid, that would be known as condensation. And actually, condensation is the exact opposite process from vaporization. And in fact, it involves the same amount of energy, except for vaporization, you're putting the energy into the substance in order to get it to go from a liquid to a gas. And in condensation, you're pulling energy out of the substance to get it to go from a gas to a liquid. But the amount of energy is the same, as long as it's the same quantity of the same substance. So if you wanted to vaporize in a gallon of water, you'd have to put in a certain amount of energy. If you then take that steam, the amount of steam produced from that gallon of water, and condense it back into a gallon of liquid water, you would have to take out that same amount of energy. There's a process that can go from liquid to solid also, and that's freezing or solidification. And again, that process is exactly the same as melting or fusion, only in reverse. So if you had, say, a pound of ice and you wanted to turn it into liquid water, you would have to put in a certain amount of energy in order to melt it into liquid water. If you then wanted to take that liquid water and turn it back into ice, you would have to remove that same amount of energy. And so the process, any process on this chart that goes from left to right would be endothermic. So any of the processes that goes from left to right would be a process that requires you to put energy in to the substance. And any of the processes that go in the opposite direction would be exothermic processes, that is, processes in which the substance releases energy. And we're not actually done yet, because it is possible to sort of cut out the middleman and go straight from solid to gas. So there is a phase change that will do that, and that is known as sublimation. That's, for example, what dry ice does. Dry ice is called dry ice because it doesn't leave a puddle behind when it warms up. It just goes straight from solid to gas. Solid carbon dioxide to gaseous carbon dioxide in the case of dry ice, and that's sublimation. Actually, regular everyday water-based ice sublimates to some extent. If you try to maintain ice in your ice trays in your freezer, you may notice that you have to keep filling up the ice tray every so often, even if you don't use the ice cubes, because the ice cubes keep shrinking on you. And that's because of sublimation. The ice is going directly to gaseous water vapor in the freezer. It can't go to liquid water because the temperature in the freezer is constantly below the freezing point of water. But the water can sublime below the freezing point of water, and that's why your ice cubes are disappearing. And there is an opposite process where a gas can go directly to the solid without becoming a liquid. And in fact, that's why you have to defrost your freezer every so often, because of the subliming ice cubes and ice from other things in the freezer. The ice goes directly from solid to gas. Well, that water vapor is then circulating around inside the freezer, and eventually it touches the cold walls of the freezer, and instead of condensing the liquid because the temperature is below the freezing point, it goes directly back to solid ice. So your ice cubes are basically subliming into water vapor, and that water vapor is then depositing itself on the walls of the freezer. And again, that's why you have to defrost it every so often. And that is known as deposition, because the water vapor is depositing itself as a solid on the surface. Phase changes. These phase changes will be discussed in more detail later in the chapter. And phase changes can be accomplished by changing the temperature. That is by adding or removing heat. And so going between liquid and gas in either direction can also be done by changing the pressure. And so it turns out that increasing pressure favors the more dense state. And of the two, liquid and gas, that would be the liquid. Decreasing the pressure favors the less dense state. Which would be gas. So you can actually boil water by putting it under vacuum. It's actually kind of impressive to watch water boil just because you're reducing the pressure on it. And you can touch the container and it's cold. So and another example of that is a butane lighter. If you buy one of those cheap disposable butane lighters, particularly one of the ones that's transparent, so you can actually look right through the plastic and see that there's a liquid inside. But yet when you open the little valve on it, no, assuming that you haven't made a spark so there won't be a flame, you can just open the valve and no liquid comes out. And that's because what's inside the lighter is butane. At room temperature and room pressure, butane is a gas. But if you put butane under even a little bit of pressure, above, normal atmospheric pressure, it condenses into a liquid. And that's what's going on inside the lighter. You'll notice that the plastic walls of the lighter are fairly thick so that it can maintain enough pressure to keep the butane in a liquid state. But when you open the valve on the lighter, the butane is now exposed to atmospheric pressure, and so it becomes a gas as it leaves the lighter. Okay, well, we're over 30 minutes now, so I'm going to cut there, and then we'll go on to segment B in just a moment.